Securing a traditional application is like guarding a single apartment. You have one front door, you lock it, you check IDs at the front, and once someone's inside, it's trusted. Easy, right? But securing microservices is like trying to secure an entire city. Suddenly, you have thousands of doors, windows, and streets. You can't simply use the same logic of securing one building to secure an entire city because it puts your system at massive risk. So today I'm starting a brand new series on microservices security. Over the next few videos, we're going to break down exactly how to protect these complex systems without slowing down your development. In this first part, we're going to look at why the old way of doing things like monolith is dead, what a microservice is, and the challenges you will face when you switch to microservices, and how the API gateway becomes your new best friend. But before we can build a defense for our city, we need to understand how we used to protect the apartment, and why it was so much simpler. Back in the day, we built monoliths. We can think of a monolith like a building with only one or two doors, usually port 80 for HTTP and port 443 for HTTPS. You only need a few soldiers at the front door to keep the place safe. When a request comes in, it is a servlet filter or an interceptor or middleware at the entrance. This filter is the bouncer of your app. It does all the heavy lifting. It checks your ID, verifies your session, and makes sure you're allowed to be there. If you don't have an active session, the bouncer stops you right there and challenges you to log in. Once you're past that front door, you enter what we call the circle of trust. Well, inside a building, the order component needs to talk to the inventory component. Since they both live inside the same process, like the same Java virtual machine, they talk to each other directly in memory. This is called an in-process call. It's incredibly secure by default because there's no network for a hacker to sit on and listen to the conversation. Because of this, these internal components trust each other implicitly. The inventory component doesn't ask for your ID again because it assumes that if you're already past that middleware, you're good to go. Your identity is simply inside a shared web session, making your name, email, and permissions available to every part of the app instantly. It's simple, it's fast, and it's very straightforward. But when components become separate applications that need to talk to each other, everything changes. So if the monolith model was so secure and manageable, why did the industry shift? Why did we move away from a model that was easier to protect? Well, the answer is in the scalability and development velocity. In a monolith architecture, the entire application is a single unit of deployment. If you need to update a single function, you have to rebuild and redeploy the entire codebase. Also, you can only scale the application vertically by giving more resources to it, or horizontally by replicating the entire monolith, which is incredibly inefficient when only one specific component is under high load. So what is a microservice? Technically speaking, a microservices architecture decomposes a single application into a suite of small independent services. Each service runs its own unique process and communicates with others using lightweight mechanisms, typically an HTTP-based API or message brokers. Instead of a single massive binary, you have a distributed system of components, one for identity, one for payment processing, and another for inventory management. This shift provides three critical technical advantages. First is independent scalability. You can scale specific services horizontally based on their individual resource demands, like CPU, RAM, or I/O, without affecting the rest of the system. And the second is different services can be written in different languages like Java, Go, Python, and use different data sources like NoSQL, relational, or graph. And the last one is isolation of failure. A memory leak or crash in one service is contained within its own process boundary, preventing a total system outage. In a microservices architecture, the internal interaction becomes remote procedure calls or REST API requests over a network. We have moved from safety of a local memory to network communication. Every time one service talks to another, the data is transmitted across a wire, which introduces new risks like interception, tampering, and unauthorized access. This brings us to the primary challenges that make securing a distributed environment a massive issue. Breaking a monolith into microservices solves scaling problems, but it creates some massive security issues that every engineer needs to understand. First one is a broader attack surface. In a monolith, internal communication happens inside the memory of a single process. But in microservices, every time one service talks to another, it's a remote call over the network. Each service now exposes its own entry points, meaning you no longer have one front door to guard, you have hundreds. And remember, your system is only as strong as your weakest service or weakest link. The second issue is screening latency. In the old model, you check the user's credential once at the entrance. In microservices, every single service must perform its own independent security screening. If every service has to call a remote security token service just to verify a request, your system's performance will drop. The next issue is bootstrapping trust. If you have 100 services, they all need a way to prove who they are. This usually means managing thousands of certificates and keepers. And if you don't have massive automation to handle the rotation and revocation of these keys, managing that trust becomes an operational nightmare. The fourth issue is the difficulty in tracing requests. When an error or a security breach happens in a monolith, the stack trace is all in one place. But in microservices, a single request might hop through 10 different services. Without complex distributing tracing tools like Jaeger or Zipkin, you're essentially blind to how data is moving through your system. The next issue is user context sharing. Well, monoliths use a shared web session, but microservices shares nothing. You have to pass the user's identity, which we call context, from service A to service B to service C. So you might use tools like JSON Web Tokens to make sure that context hasn't been tampered with by a man in the middle. And the final problem is polyglot architecture and expertise. Because microservices allow different teams to use different languages like Go, Java, or Python, you can't rely on one central security team. Every development team needs their own security expertise to understand the specific vulnerabilities of their own tech stack. So it's a lot to manage, but these challenges aren't impossible to solve. In order to solve them, we have to go back to the fundamentals of security and apply them to this new distributed system. Before we get into the tools, we need to talk about security fundamentals. First one is authentication, which talks about who you are. This is about identifying the caller, whether it's a human, a system, or a system acting on behalf of a human. For humans, we use passwords and MFA, but for system-to-system calls, we rely on certificates or JWTs. If a web app is calling a microservices for a user, OAuth version 2 is the industry standard for delegating that access. The second one is integrity, which is about was the data changed or not. We need to ensure that the data isn't intercepted and tampered with. We use digital signatures to detect changes and TLS to protect the data in transit. This also applies to your logs. If an attacker can modify your audit trail in Jaeger or Zipkin, you'll never know who they were. Third one is non-repudiation, which is about can you prove something that they did or not. This ensures that a service can deny an action it took. If a microservice signs a transaction with its own private key, it's legally and technically accountable for that action. By keeping a record of these signed transactions and timestamps, we ensure full accountability. And the fourth one is confidentiality, which is about who else can see this. We must ensure that only the intended recipient can read the data. We use encryption at rest for databases and in transit with TLS. But a quick warning, we have two concepts in TLS, TLS bridging and TLS tunneling. You should be careful with TLS bridging, because this is where proxy decrypts your data to inspect it, meaning it's in clear text for a while inside that proxy. So if you need total privacy, you need TLS tunneling, where the tunnel is end-to-end. The next fundamental is availability, which answers the questions of is the system up or not. Security isn't just about hackers, it's about making sure legitimate users can get in. The good news, in microservices, if one service crashes, the whole system doesn't have to go down. And the last principle is authorization, which is about what you're allowed to do. Once we know who you are, we have to decide what you can touch. In this architecture, we usually do this in two stages, coarse-grained and fine-grained. In this architecture, we usually do this in two stages. Coarse-grained checks at entry points, which talks about can you enter the system at all, and we have fine-grained checks inside the specific service, which talks about can you edit this specific record or not. Well, understanding these principles is great in theory, but where do we actually enforce them? For most modern systems, it all starts at the very edge of your network. In the microservices architecture, we don't just leave our services hanging out on the public internet. Instead, we use an API gateway. Think of this as a front door for your entire system. The gateway acts as a centralized policy enforcement point, which its job is to handle the non-functional tasks, things like security, throttling, and logging, so your microservices can focus purely on business logic. When a request hits the gateway, the first step is to identify the caller, and we have two ways here. First one is mutual TLS, or MTLS, and the next way is OAuth version 2. This is the standard for delegated access. The gateway validates security tokens to ensure the application has the right to act on the user's behalf. And we will talk about these concepts deeply in our next videos. Gateway also handles the coarse-grained authorization. These are the high-level rules. For example, is this user allowed to access the payments API at all? If they fail this check, the request never even reaches your internal network. We leave the fine-grained stuff, like can this user edit this specific record, for the individual services later on. And once the gateway is satisfied, it has to hand the request off to an upstream microservice. But how does that service know who the user is? We could use simple HTTP headers, which are easy to spoof, but the better way is to use a signed JSON Web Token or JWT. The gateway, or an internal security token service, creates a cryptographically signed token containing the user's identity. Because it's signed, the upstream microservice can verify it instantly and know exactly who it's talking to without needing to re-authenticate the user. Well, securing microservice is a huge shift from defending the old monolith model. We've moved from single cycle of trust to a zero trust environment where every service has to be defensive. This was just an introduction, and in the next videos, I'm going to talk about JSON Web Tokens, which is the fundamental concepts in microservices. If there's any questions about the topics, let me know in the comments. Don't forget to like and subscribe. See you in the next one.